Okay, I think it's time to get started. Not so many people in the room, but probably the Netflix guys are a little bit more attractive. Can someone maybe close the door? Thanks a lot. So, hi everyone, welcome to this talk about Polyglot Gradle. In case you haven't seen me at the conference yet, my name is Niederwieser. I'm an engineer for Gradleware. Also have my own open source project, which is called Spock. Used to hack around in Groovy in former times. I'm based in Linz, Austria. Austria is this little country between Germany and Italy. Little but beautiful. And if you want to reach me, that's my email. And I also do some Spock promotion over Twitter from time to time. So if you're interested in that, check me out on Twitter as well. So what is this talk about? It's basically about our support for Jvm languages and a little bit about other languages as well. We decided to switch out one thing because initially we decided to talk more about Clojure and less about Java. But eventually we've been told that there are quite a few people out there who still do Java. And actually Gradle brings quite a few things to the table in terms of Java support. So we'll talk a lot about Java and Groovy and Scala because they are the languages that have first-class support in Gradle. If there's some time, I'll shortly tell you what third-party plugins there are. Maybe you have listened to today's talk about C++, so there's exciting stuff coming up in the C++ space. But in this talk, we'll focus mostly on Java, Groovy, and Scala. And I have a couple of demos, and along the way, we'll talk about such things as compiler daemons, joint compilation, incremental compilation. All of these features are supported in one way or another, or leveraged by Gradle, but probably not so many people know about it because it usually happens under the hood without you having to do a lot about it. So let's start with Java. And it's still pretty relevant, I think. Even if it's not the hippest language anymore, it's still the most used one, at least on the JVM. And let's see what Gradle provides there. If we start very low level, there's a Java compile task. That's our interface to the Java compiler. Usually you don't declare that directly. You rather apply the Java plugin or something like it. But it's not unusual to configure it directly. So if you need some fine-grained control over Java compilation, you can always configure it on that level. And I've listed some of the most popular configuration options. So for example, you could set the class path of the compile Java task. Usually you just do that in the dependencies block, and from there it gets mapped to the compile Java task. But if you need finer-grained control, you can set the class path or mutate it directly. There's the destination tier where all the class files go. That's also quite an important information, and that's the default. By default, we compile under build classes main if it's the production code. And then there are the source compatibility and target compatibility settings. And this is about which version of Java you target. So source compatibility is which language features you want to use. For example, if you want to use, let's say, lambdas, Java lambdas, and you'll have to set it to at least 1.8. And of course, you also need a 1.8 JDK. If you want to use generics, you have to set it to at least 1.5. And then there's the target compatibility. That's the runtime you are targeting. And it defaults to the same as source compatibility. So it's quite common that you will set both of them to the same value, and in that case you can just set source compatibility. Actually, it's not quite true on the task, but the same properties also exist on the top level in your project, and there it's usually enough to just set source compatibility. But for example, if you want to target the 1.5 language but run on JDK 6, you could set target compatibility to something higher than source compatibility. So that's the base settings, and then there are the classical compiler settings, which are most of the things that you could also pass in the command line to a Java C. And there's a separate section, it's compile java.options. And there you can set a lot of options that you will also find for the command line compiler. So let's have a look at some of them. There are many, many more, and you'll find them in the DSL reference. But a few useful ones are the source encoding. That sometimes people have problems with that. because it defaults to the JVM's platform encoding, which is not UTF-8 on all JVM platforms. So if you want to make sure, you have to set compile or tasks with type Java compile.options.encoding to, for example, UTF-8. So if you get lots of strange compile errors with lots of strange symbols, then maybe this will save you. You can control how much debug information you generate. You can here set it to true or false, but there is also another option which is more fine-grained, like do you want to set a table for debug table for local variables and this kind of thing. You can run the Java compiler in process or in a separate process. By default, let me see, we still run the Java compiler in the Gradle JVM, but the larger the code base is that you want to compile at once, the more it helps to set fork to true. And then you run it in an external process. And once you do that, you can configure that external process. For example, if you want to compile with an IBM JDK but run Gradle with an Oracle JDK, then you can set the executable to some other Java C. Important setting is the memory. If you have a large source base that you compile in one go, you'll likely have to crank up the memory. And then there are other options, and then you can also pass arbitrary JVM arguments. So anything that you can pass on the command line. If it's not modeled in Gradle, you set this JVM args property. What else do we have in terms of options? There's the use and this is because like say a year ago when we did Gradle 1.0, our compile task would actually call the and Java C task. So we just wrapped the and task, and the and task did the heavy lifting of integration with the Java compiler. That's no longer the case. We now have our own native integration, which uses the JDK compiler API. If you're running on JDK 6 or higher, we'll use the JDK compiler API. If you run on JDK 5 and you say use and false, we'll try to use the proprietary Sun compiler API. And otherwise, we'll fall back to and. Yeah, so that's no longer, so the default is now to use the native integration, use and is equals false. You can still drop back to true, but if you need to do that, if you in your build script have use and equals true, then please let us know why. It would be really interested why, if that is, why you can't use our native integration. The use and flag is deprecated and will likely go away in 2.0. So in 2.0 there will be no fallback to the and compiler, and we better know all the problems beforehand. So please, if you have a reason to use our old and back end, then let us know why, so that we can improve our native integration. Yeah, with the compiled Java, you get the usual up-to-date check, like you get them for many other Gradle tasks. And this is not specific to compiled Java, it's a generic mechanism. For those of you who are aware of that incremental build feature that Gradle provides, the idea is it holds for every task basically. It only runs again if its inputs or outputs have changed. For the compiled Java, this means the inputs are the source files, things like the compile class path and all the compiler settings you've seen. If any of them changes, the task runs again, which means it redoes all its work. It's just a flag, like either it fully runs or it doesn't run at all. Likewise, if you remove its class files from the previous one or tamper with them, then it will detect that and run again. The important thing is that this is not incremental compilation. So Gradle's incremental build feature is something different from incremental compilation. When people talk about incremental compilation, they usually mean when you only change in your source tree that gets compiled together, you only change a single source file, then the compiler figures out it only needs to recompile this source file and other source files that depend on this one, but not the whole source tree. And for Java, we don't currently have that. Many people think that the Oracle JDK compiler can do incremental compilation, but it cannot. Eclipse compiler, for example, can do it, but Oracle compiler, you always have to tell it exactly which source files to compile. And it cannot figure out that it only has to compile a subset of them. That's a common misconception. Usually it's not so much of a problem because Java compilation is really, really fast. I mean, it's amazingly fast. Only if you have an extremely huge code base and it's not modularized, then you might want to have incremental compilation. There is a chance that JDK 8 will come with an incremental compiler. If that happens, we'll integrate it. And I'll tell you later of another trick how you can get incremental compilation with Java today if you really need it. So which Java compiler? That's also a question. You know, often you run with one Java version and want to compile against another version. Maybe even against the Java 5 compiler, although Gradle is already running with JDK 7 or something like that. So by default, Gradle will use the same Java compiler version as the JDK you run Gradle with. So you set, for example, your Java home, you start the Gradle build, and the same JDK will be used for the Java compiler. Now, what do you do if you want to have, your developers already have JDK 7, but on your CI server you also want to compile against JDK 1.5 because your target environment has to support 1.5. The simple solution, what we do on CI, is that we have a Java build against 1.5, 1.6, and 1.7 for Gradle because we support Java 1.5 runtimes, and we simply configure CI to run whole Gradle with the Gradle build 3 times with JDK 1.5, JDK 1.6, JDK 1.7. And by that you get the JDK 1.5 compiler. If you run Gradle with 1.5, you also get the Java class library 1.5, so you will hit cases where you inaccidentally use a Java 7 API that would not be available in your Java 1.5 runtime. So that's the easiest option. Another option is you can, of course, configure this source target compatibility flag that we've seen. That's also what many people do. So they set source and target to 1.5, even though the Gradle runs with 1.7. The only thing here is you also should set the boot class path of your compiler, because otherwise you are producing something that can run in Java 1.5, but maybe you are using a 1.7 API, and that won't give you a compile error if you compile it with JDK 7. So if you want to catch that as well, you can configure the Java compile task with the boot class path for a JDK 1.5, or you run whole Gradle with an older JDK. Okay. Or you have good tests, and you are okay with not finding those things at compile time, but rather at runtime. We've already seen, for example, if you want to use an IBM compiler, the easiest way to, don't want to run Gradle with the IBM JDK, the easiest way is to set this fork options.executable and point it to some other Java C, like the IBM one.
What would be the best option to allow developers to set their own executable? For example, if they're running different operating systems, the path is different. Would it be like environment variable, or would you recommend something?
Yeah, for example, an init Gradle, where they could set a variable, and then in here you say fork options.executable equals that project property. That would be a simple solution for something like that, if you really want that. Yeah, in general, we try to make the build self-contained, so that it's not necessary to set things here and there, and otherwise it doesn't run. Because as soon as you set something up per developer, the build becomes less portable. Then some other developer, the build fails, and then he figures out, oh, I have to set this in my user home or there. But if you need it, you can. There are several ways. Put it in a properties file in init Gradle, and then reference it here. Okay, that's so much for the Java compile task. Now we move one level up to the plugins, because usually you more say apply plugin Java and don't fiddle around with the tasks. So there are actually two basic Java plugins, the Java base plugin and the Java plugin. The Java base plugin, that's about baseline Java support. It provides some capabilities and not so much defaults. So for example, the Java base plugin introduces this language here. So this part of your build script is only available. You can only declare source sets if you apply Java base. Usually you don't apply it directly, but transitively. For example, you apply Java, and Java in turn applies Java base. So it provides this capability to describe different sets of sources and related information. So for example, here we declare a source set called main, and by that we mean our production source code as opposed to our test code. And we set up its Java source directories. These are all the defaults that I'm listing here. So you wouldn't necessarily have to configure that if you use the Java plugin. You set a source directory to source main Java. You can set multiple. You can set excludes so that you only compile certain packages and not others. That's sources by themselves, and then there's additional information related to the sources. For example, the compiled output of these sources, where should they go? Because one source set will usually be compiled together. So all Java code in one source set will be compiled by one compiled Java task. If you declare 3 source sets with Java sources, you will get 3 compile tasks out of that. So you can configure where the classes go, you can configure where your resources go, and then if you have a jar task, the jar task will use these two things and put them in a jar. You can also add further directories there. For example, if you have, if you, let me see, what's that? Let me see. Here, that's a little bit strange. So let me think about it. I should know what's on my slide. Oh yeah, these are some generated resources. So if you generate some resource files and want them in the jar as well, you can register further directories, and they will automatically go in the jar as well. And some IDEs can figure out these things as well and put them on the class path of the IDE. The last two important bits of information that belong to a source set is the compile class path and the runtime class path. So anyone that wants to compile that source set, any task, will then use that compile class path, and any task that wants to run it in a way, like for example, run the tests, if that's a test source set, would use that class path. And by default, they default simply to the configurations. So if you say dependencies compile something, so you set up an external compile dependencies, then this will automatically, here, by this default, go on your compile class path. So that's the general capability you get by the Java-based plugin. But typically you will rather use the Java plugin. So the Java-based plugin does not add any source sets, but it adds configuration rules. So whenever you add a source set, like this main one, you get a lot of things for free with the Java-based plugin. What do you get for free? 3 tasks per source set, compile Java, process resources, and a task that is just the sum of the two. You get 2 configurations so that you can set compile and runtime dependencies, external ones, for that source set. You get, for a Java-based plugin, you get also a few global tasks, like for example build, this Gradle build. This comes from the Java-based plugin. If you wouldn't have that applied, you couldn't say Gradle build, for example. And it also adds some properties to the build script, to the outermost level of the build script, namely the source compatibility and target compatibility. So you don't have to set them for each of your compile tasks separately, but you can just say on the outermost level source compatibility is 1.5 or target compatibility is 1.6. So that's the kind of thing you get with the Java-based plugin. Now let's step it up one bit, Java plugin. This is what you typically apply when you build a jar. You want to build a simple jar. It's a bit of a misnomer. It should probably be called Java library plugin or something, because that's what it is. And it's an opinionated way. It's kind of Gradle's Maven way to build a jar file. So if you're happy with lots of conventions, and for many people these actually are a good fit, then by all means just say apply plugin Java. What does it do? It adds exactly 2 source sets, one for your production code and one for your test code. That's the basic assumption. And then it adds a few additional tasks, a jar task to create a jar, a test task to run those tests of the test source set, and a Java doc task to create Java doc of your production sources. And if you're lucky, all it takes to build a library is just this kind of build script. So you apply the plugin, and typically you will have some external dependencies. So you will first have to set up a repository and then a dependency. And in the simplest case, that's already it with the Java plugin. You can easily add further source sets. For example, many people also keep integration tests or acceptance tests in the same project. And then they additionally, to the ones that are already brought in by the Java plugin, declare an additional source set intake test. And that would then look very similar to this, except that it would say source sets intake test and would choose some different source directory, but otherwise it would look very similar to this. So adding is okay, but if for some reason you are not happy that there is a test source set, because you will also get tasks for that, right? A task that compiles it and so on. If your structure is completely different, then what we've seen with some clients is that they don't use the Java plugin. That's the whole idea. If the conventions are a complete misfit for your situation, don't use the Java plugin, only use the Java-based plugin and build your own My Company Java plugin. If you look in the Gradle source code, the Java plugin is like, I don't know, at most a page or half a page. It's very, very simple because it just declares a few simple tasks and 2 source sets. The Java-based plugin, which introduces the whole concept of source sets, this whole language, is much more complicated. And so the idea is we separated the two so that if the conventions don't make fit for you of the Java plugin, then you can replace that and still get all the general capabilities for building Java code. Yeah, there are other Java-related plugins that build on top of Java. So if you build a web project, that's WAR, that also applies Java, which applies Java base. The ear plugin, if you build an ear, if you have a Java library and want to package it up, so you want to have a Java library with documentation in a zip file with all its dependencies, also in a lib directory, so a complete distribution of your library, then you will apply the Java library distribution plugin, and they all build upon the Java plugin, which builds upon Java base, which builds upon the compiled Java task we've seen in the very beginning. So that's the basic way how you build Java code with Gradle and what we support. A recent an addition we made maybe a year ago, we didn't have it in 1.0, but we have had it for quite a while, is a so-called compiler daemon. Before we had the compiler daemon, the problem was, why did we always run Java compilation within the Gradle JVM? Because otherwise we would have constantly to fork a new Java compiler. And if you have a huge multi-project build, you can easily have 100 compiled Java tasks. And if you start up 100 Java compilers, you lose a lot of time just starting Java compilers instead of compiling. So instead we did everything in process, but then if you have a huge source tree, in process is also not so nice. You need to crank up the memory of your Gradle JVM a lot, and we generally made the experience that if tasks need a lot of memory or a lot of other resources, we should run them in an external process, not in the Gradle JVM. So with the compiler daemon, you get the best of both worlds. The compiler daemon is an external process, but it's reused. So currently it's reused within one build, not across builds. But if you have one Gradle build which has 100 compile tasks, it will once fork a new Java process and run all 100 Java compilations in that one process. So it makes the whole thing more stable, and at the same time you only have to fork once. Yeah, and interestingly, even for Java, that can result in significantly faster compilation, because, especially compared to forking each time, not only because you save the startup time, but also because the Java compiler is written in Java, and the longer you run it, the more optimized it gets, the more code gets compiled, gets jittered, and even the Java compiler, if you compile something very huge, you can see the difference if you reuse it as much as possible. Even more importantly, the compiler daemon is also used for Groovy and Scala, and for those languages it's even more important, because then we always compiled out of process from the beginning. We didn't have a good experience, for example, with Groovy, letting that run within the Gradle JVM, so we always compiled them out of process, and there the speed gain by reusing this compiler daemon is even more dramatic. Okay, that gets me to the first daemon, Java compiler daemon. So let's have a quick look at a project. I just have to choose the right one. So let me see. Yeah, this is it. So this is the official Spring integration project, and that contains only Java code, and we'll compile it a few times. And first of all, we tell it to use AND. That's no longer default, but we switch back to that, and we tell it to fork. And then we'll see what kind of performance we get with that. Okay, Spring integration. So we do Gradle W clean build or clean compile Java. Maybe even better, clean compile Java, so that we only redo the compile Java bit. So here you see the deprecation warning that use AND will go away. At the very top you saw that. Okay, it takes a bit. They have like 20 sub-projects, Spring integration. And you see the AND Java C messages, the warnings, because we really call through to the AND Java C task here. And here, this warning here, the bootstrap Classpath not set, that's what you get when you compile. I'm using JDK 1.7, so I'm compiling with the Java 7 compiler. I am setting source compatibility to 1.5 because that's what the Spring guys do, but I'm using the JDK 7 class library. So if I were accidentally to use a API that's not available in Java 1.5, I wouldn't notice it at compile time. And Java C doesn't like that and thinks that's a bad idea. And so that's why it wants me here. Actually, they're using 1.6 source level. But I'm using a 1.7 class library. Okay, so 53 seconds. Probably would get a little faster if I ran it again. I think last time I ran it was more like 45 seconds. Okay, and now let's stay forking, but use and false. So our native integration, and that will, since we fork, it will automatically use the compiler daemon. And hopefully it will now be faster. Otherwise I'm host. Yes, so 53 to 16. I am not to blame and here. Lots of that is because we fork for every process. But we even saw that our compilation for some reason is faster than calling the AND task, and probably it's because the AND task does some checks that we do as well. So if we use AND, we do some things twice, and so it's in that case it's not AND's fault, but with our native integration and the compiler daemon can make quite a difference. Currently, the compiler daemon goes away after one build, so it started anew for each build invocation, but we have plans to make it like cross-build, so that it stays around like the Gradle daemon, because there are use cases like Scala, to which we will get later, where you would like to reuse the same Scala compiler across Gradle invocations. Okay, so what's coming for Java? At least these are things that some of them we're already working about, other of them we are talking about. So I can't make any promises here, but this I think is the things we'll see maybe in the next year in our Java support. First of all, we are redesigning that source set model. You remember that source sets block where you can declare all those sources? It's a nice declarative element, but we found out that for very advanced use cases, it's still not flexible enough. And specifically Android. If you're familiar with the Android plugin, the Android plugin also has a concept of source sets, but they more or less re-implemented it. They're not using our source sets, they're using the source sets in the Android block, which are their own abstraction. Similar, but still not the same. And so we are working on the side on a new source set model. The old one will still stay around. That's even more flexible. And the main difference is that right now, for each source set you declare, you get a few things for free. You get a compiled Java task, a process resources task, and so on. And in the future, this will be more flexible. So you will declare your source sets on one hand and your binaries on the other hand. And then you will describe the transformation from the sources to the binaries. And this will allow you to model such things like I have the source set that make up the free part of my application and the source set that makes up the premium part of my application. And when I build the premium jar, then I want to, in the end, have them together in the same jar. And right now, this is not so nice to describe with our source sets. So in the future, we will describe a mapping from source sets to binaries. Binary could be even the classes directory, a jar, a var, such things, a zip. This is a binary, and you describe the mapping, and based on the mapping, Gradle then generates tasks. So it also takes account the binary information for creating tasks. And another focus is that we want to make our source sets easily extensible to other languages. So for example, now the Closure people, they implemented a third-party Closure plugin, and it was quite hard for them to make our source sets work for Closure. They managed to do it. It's not rocket science, but it's not as nice as it could be. And so we are improving the API so that whenever someone else writes a third-party language integration, it's very easy to reuse all the nice source set stuff that we have. Reuse compiler daemons across builds, I already said that. Smarter up-to-date check. So right now this is all or nothing. So if anything has changed, we recompile everything. And also, if anything upstream has changed in a multi-project build, we see our compile class path has changed and rebuild everything. And we could be much smarter there. For example, if you have an upstream project and an internal class was changed that we aren't even allowed to reference, then we wouldn't necessarily have to recompile our stuff. So we can be much smarter than all or nothing. And even smarter than that, that's incremental compilation. we'll see whether we ever have to implement it on our own. We still hope for JDK 8 because there are some rumors that it will have an incremental compiler. And there is a neat trick. If you really, really want it now and you're open for some adventure, you could use our Scala compile task to compile your Java code. And the Scala compile task uses sync, the incremental Scala compiler, which is incremental for Scala and as a byproduct also incremental for Java. So if you pass that guy only Java, then you should get a cross-project in a multi-project build, incremental Java build out of that. So I've tried it with some toy project and it worked, but it's definitely a kind of experimental feature, but it's probably the best you could do today if you needed incremental Java compilation. Most of the time it's not such an issue because, as I said, Java compilation is so blazingly fast and usually your bottleneck is elsewhere. Ooh. Okay. So let's move on to some other language. Next language, Groovy. Since Gradle is to some extent based on Groovy, we of course have good Groovy support. Probably the most sophisticated Groovy support of any build tool I know at least. And again, it starts at the bottom. We have a Groovy compile task, which is our interface to the Groovy compiler. First twist, it can compile Groovy and Java. This is because it supports joint compilation, and we'll see that in a bit. So the task is structured very similar. If you ever need to declare one yourself, there's also a Classpath and other settings like for Java compile. This important thing to know is if you want to configure the Groovy compile options, there are two kind of options. The same options property, but that's the Java compile options for the joint compilation case, where you compile Groovy and Java together. So if you want to set Groovy compiler flags, you have to use the Groovy compile options and then set something in there. That's easy to get wrong because if you don't spot this one, then you might think that the options are the Groovy compiler options, but actually they are the Java compiler options for the joint compilation case. So what can you set there? Very similar encoding. You can again set it. You can fork. We fork by default for Groovy. If you want to pass other source files, if you implement some special DSL in Groovy, that you could have files that have an ending other than Groovy, but still be valid Groovy files, then you have to set the file extensions to something and add something there. Otherwise, the Groovy compiler will not look at them. There are a few optimization options that the Groovy compiler takes, and probably the most important one is Indy. And if you set Indy to true, then and you run on JDK 7 or higher, then you'll get a version of Groovy that uses the invoke dynamic bytecode instruction. So there is a separate distribution of Groovy which does all its dynamic method dispatches with invoke dynamic, and that already in the latest version gives you quite some speed up. And you still have the same dynamic Groovy, it's just faster. Only drawback is that if you compile with that thing, you can only run on JDK 7 or higher. And again, our old integration used to be based on AND, but by now we have a native integration. And this one is also scheduled to be deprecated, to go away in 2.0. Up-to-date check is exactly the same, so it's all or nothing. And if nothing has changed in terms of the inputs and the outputs are still the same, you will get this compile Groovy up-to-date. So how do you decide which Groovy compiler you choose? And this is quite convenient by now. You simply set up a compile dependency on Groovy because you need it on your compile class path anyway, because you want to use the Groovy library. And from that we infer and use the same thing for the compiler. So you don't have to separately, as it used to be necessary, tell it which Groovy compiler to use. It will simply use that thing both to run the compiler and it will put it on it will compile against that library as well.
Is that the default? There?
Yeah, that's the default. There's still the old way to set here dependencies Groovy instead of dependencies compile, and we still support that as well. But the Groovy configuration, I think it's deprecated by now. So if you come from, I think, Gradle 1.2 or so, then simply replace Groovy with compile. So instead of saying dependencies Groovy something, say dependencies compile something. The nice thing here is that you can target this now per compile task. So for example, if you have Java production code and Groovy tests, then you say here dependencies test compile, and then you only get the Groovy library on the test compile class path. With this Groovy thing, you always got the Groovy library on the compile class path. So then if you had Java production code and Groovy tests, you would still have Groovy on the compile class path of your Java production code, at least at compile time, which wasn't very nice. And now you can strictly separate that, and if you just say dependencies test compile this thing, then your main production code will never see the Groovy jar.
And that at Indy is indicating that you're using Indy?
Yeah, that's a separate distribution. That's a classifier of that Maven dependency. So you get a different jar of Groovy, namely the Indy one.
So if I don't specify dependencies and I say that I want to use Indy, it automatically will download that, or do I have to specify dependencies?
You have to specify it, yeah. I'm not sure if this one actually can do the old thing. Maybe it can. Yeah, so the answer is you have to do both things.
You do?
Yeah.
Okay. And that's whether you use Indy or not? So I always have to declare a dependency there?
Yeah, that's a good question. I'm actually not 100% sure if this means that the compiler itself uses Indy. I'm not sure if the compiler, non-Indy compiler can create Indy code. So I think you have to use either not set Indy and not use the Indy jar, or set Indy and use the Indy jar.
Right.
But it's actually a good question. I'm not 100% sure. I could give it a try. But we don't automatically infer one from the other. We don't look inside this dependency declaration and use it to set the flag or something. We don't do anything like that.
But regardless, do we have to set a dependency at all, or does it automatically infer one for by default?
No, you always have to set one, otherwise you get an error. So we don't do this thing because Gradle ships with Groovy, so we could use, if you don't specify it at all, use the one that ships with Groovy,
yeah.
But we decided not to do that because we wanted to keep it strictly separated, and which version of Groovy Gradle uses is a bit of an implementation detail. So if we ship later with a newer version of Groovy, then suddenly you would compile your code against the newer version, and we think that we should keep the two things separate.
Yeah.
Okay, there's again the same architecture with the Groovy base plugin, base capabilities, and Groovy plugin, the opinionated plugin on top of that. And the Groovy base plugin adds a little bit. You can now talk about the Groovy source code of a particular source set. You can not just say sourceset.java, but with the Groovy base plugin you can suddenly say sourceset.groovy. And also for each such source set, the Groovy base plugin adds a Groovy compile task. And it builds on top Java base, so you often see this stacking. Gradle plugins never inherit from each other. They use composition rather than inheritance. So one plugin applies another, and this forms a chain. So then the Groovy plugin, how does it usually look like? In the simplest case, it's just like that. Apply a plugin Groovy, then set a compile dependency on some Groovy version, and that is the version that will be used for the compiler, and also the library version that will be on the Classpath, so to compile against. So very often that will be enough in terms of your Groovy configuration. So now an interesting thing, what's Groovy Java joint compilation? What we support, or Groovy support, is that you can mix Java code and Groovy code as you like. You don't have to do one compilation unit has to be Java code or Groovy code, and the other compilation unit has to be pure Groovy code, but you can mix it on a class level. So in the easiest case, you put the classes in the same source directory. So for example, here we have an example, we have a Java-based Java class, like this, and in the same directory we have a Groovy class that inherits from the Java-based class, and then in the same directory we have another Java class that inherits from the Groovy class. So this is about as bidirectional as it gets, right? Java derives from Groovy, derives from Java. Could also be a usage that Java base uses Groovy class and has a field of that type. And without joint compilation, you can only have dependencies in one direction, but not in both. And with joint compilation, you can have arbitrary dependencies between the two. Now, how does it work? You can pass any Java and Groovy code to the Groovy compile task, and these parts of Java and Groovy code files, they can have arbitrary dependencies. The Java code that you only pass to the Java compile task, that cannot have a dependency on your Groovy code. So if you need it both ways, then you need Groovy joint compilation. If you only need your Groovy code to use your Java code, but not the other way around, then you don't need it. So Groovy using Java works by default because we run the Java compile task first and the Groovy compile task later by default. But both directions only work with the Groovy joint compilation. Now, how do you tell the Groovy compiler that it should compile both your Java and Groovy code? In the simplest case, you put your Java code not under source main Java, but under source main Groovy. So you put both Groovy and Java code under source main Groovy, and that's it. All the Java code in there and the Groovy code in there can refer to each other as they like. You can still put other Java code into source main Java, but that will be compiled separately. That doesn't see the Groovy code. Some people don't like that. They want to keep their Java code in source main Java, but still want to be able to mix as they want. And then you reconfigure the source directories a little bit. So you take away all the sources from the Java source set. So now the Java compile task has nothing to do. And instead you say to the Groovy source set, my source directories are source main Java and source main Groovy. Then you can keep the usual layout and can mix everything as you like. So how does it work? It's quite an interesting problem. So how does the Groovy compiler implement that? First of all, it passes the the Groovy code in the first phase, but it only passes it. It doesn't yet create class files. And it passes it so that it can create Java source code for the Groovy code. So it converts the Groovy code that it's about to compile to Java code and writes that out to disk. Doesn't yet compile its own Groovy code. Then it invokes the Java compiler, who now compiles the Java sources and these Java stubs, the stubs for the Groovy source code, now with the Java ending created by the Groovy compile task. So the direction from Java to Groovy is now solved, because for the Groovy files we've generated Java stubs. And after the second step we have the bytecode, the class files for the Java sources, and now we can run the rest of the Groovy compilation, which can now compile against the Java class files. So that's the trick, to generate Java code from the Groovy code. That's how it works. And that works quite well. There's an interesting trick. How does when the Groovy compiler invokes the Java compiler, how does it pass it the generated Java stubs? It doesn't put it on the it doesn't compile them automatically. It doesn't tell the Java compiler these are source files to compile, but it puts them on the so-called source path. And many people don't know that a Java compiler, you can pass it dependencies in a binary format as class files. That's the compile class path. But you can also pass it source files as dependencies. So if you want to compile class A only, which depends on Java class B, you can pass that Java class B in source form as a dependency. And that's what's called a source path. And that's what the Groovy compiler uses to pass the generated stubs to the Java compiler. And because then the Java compiler will only look at these source files if some of the Java code actually references them. And that turns out to be much more robust and stable than compiling all Java stubs. So that's how it works technically. And with that, we'll get to the demo, Groovy Java joint compilation. So here we go. Okay, so a little Groovy Java application. I've used the application plugin so that I can easily run the main class that I have in here. I just set up one dependency on Groovy, and then I have 3 classes. And right now all of them are Groovy: main Groovy, ray tracer Groovy, and util Groovy. And the main file uses the ray tracer, which uses the util class. And they don't do a whole lot, but the ray tracer stays true to its origins and does a lot of method calls, but the method calls themselves don't do much. So let's give that a try. If I can find the right shell. Let's see. So here we go. Source and Groovy Java. Okay, here we go. So now let's do a full build of that thing. Okay, that's fine. And now let's run that ray tracer application. And it's all written in Groovy, right? And it does quite a few method calls. So it takes a while. Shouldn't take too long. Okay. And that's the result. That's what we computed and took us 11 seconds. And now I want to show you a practical use case for joint compilation, because you might think, why do I even need that? Why do I need to switch around arbitrarily? Can't I do one layer in Java and one layer in Groovy? Isn't that a nicer architecture anyway? But Groovy has this idea that that first of all, you can nowadays write everything you like to write in Groovy because it's a mature language. And if should you ever have a performance bottleneck, then you can write that 1% of code that's the real bottleneck, you can switch that over to Java if it's really necessary. And a ray tracing algorithm is a good example. A ray tracing algorithm basically is only method calls, and method calls is where Java still has a performance advantage over Groovy. And so the idea could be, okay, let's rewrite this class in Java. So let me just do that. I rewrite it to Java. Okay, done. I wrote it in such a way that it's also valid Java. And so now the hope is that it will be much faster. Only problem is I have now my whole code base is Groovy except for the ray tracer. And main uses ray tracer, uses util, and I already have bidirectional dependencies, right? So without joint compilation, I wouldn't be able to do that. I would now have to, all the other classes that ray tracer depends on, I would also have to port them to Java. Even though in this case, the util is completely irrelevant for performance because it's a single call. And so from my perspective, it doesn't make a sense to port util and anything else. And so you can very quickly get in the situation with a little refactoring where suddenly you really want to have joint compilation. Okay, now let's try this again. Run it. It has to compile the Java code as well, but that shouldn't be too bad. So we're running again, and hopefully in Java it's a little bit faster, half the time or something. So that's one use case. You get quicker into that situation as you think that you want to be able to have dependencies in both directions. Okay.
Now, couldn't you have just done compile static on those and
the
same performance?
Yeah, in recent Groovy versions, there's a static version of the language, and with that, depending on, in pure language speed, you get very close to Java. That's correct, yeah. But that hasn't existed for so long. And also then you can't use the dynamic features anymore. I mean, for the ray tracer, you would be glad to not to use the dynamic Groovy features if that gives you speed. But you are right. If it's a performance problem, you could even, let me think, you could even compile with one class static, because that's a per class decision in Groovy. So you in latest Groovy version, you can annotate the ray tracer class with @compile static. And then it will also be really fast. Only if it still uses the Groovy library. The Groovy library is written to make scripting easy, and so the Groovy library doesn't perform very well compared to like the Java-based class library, right? So that could still be a hit, but the pure language will be really fast if you compile it with compile static. Okay, so much for Groovy Java joint compilation, and we use that for Gradle. Gradle is built that way. We just don't care about our dependencies. I mean, we have a rule by now that we write the core in Java, but on other layers we mix and match, and everything lives under source main Groovy, both the Java files and the Groovy files. And our Groovy compiler takes care of the rest. Okay, what is there to come for Groovy? We may at some point support the Groovy Eclipse compiler, because there's a headless Groovy Eclipse compiler. And there are some indications that people are thinking to give up the Groovy C compiler in favor of the Groovy Eclipse headless compiler, because it's much smarter. It uses the Eclipse infrastructure to be an incremental compiler, for example. I'm not so excited about that, because I think every language should have a simple like baseline command line compiler, and I'm a little bit afraid about what that Groovy Eclipse compiler drags in and how complex that is if it includes some Eclipse infrastructure. But that's something that might happen. Another thing that we want to support is a Groovy REPL task, so that can easily fire up a Groovy REPL with your compile Classpath or runtime Classpath, for example. That's fairly easy to implement for us, but we don't have it yet, because to get good console support, you have to be able to deal with console programs that do formatted output, right? Like that you can loop through the history and this kind of thing. And the Gradle input-output, the console handling of Gradle isn't yet capable of dealing with that. So if you do that, you'll get some funky output if you run a shell via Gradle. Okay, now let's get to the third language, building Scala. By the way, I should have asked who is building Groovy or Scala? Scala? Okay, 2 people. And a couple of Groovy, okay. So what do we have for building Scala? Same thing again, lowest level is the Scala compile task. Our interface to a Scala compiler. Again, it can compile Scala and Java. We have the same joint compilation feature, so you can mix Java and Scala arbitrarily. And we used to be based on the Ant Scala C task, but by now our default integration, no, it's not yet the default, but our new integration is with the so-called Sync Scala compiler, and that's something that sits on top of the Scala compiler and makes it incremental. And it's also provided by TypeSafe, so it's provided by the Scala folks to get incremental Scala compilation. And the basic configuration is very similar, except that again there's the Scala compile options block. So if you want to set Scala compile options, then you have to do it in this block and not in the options block, because the options block is again for Java compile options in joint compilation mode. So what options do you have there? Some of them we've already seen. There are a few more now for incremental compilation, and usually you don't have to care about them because the Scala plugin sets it all up for you. But if you want to get more or less direct access to sync, if you happen to know sync already and you want to twiddle around, then you can set things like where the sync compiler keeps information about the state of the Scala source files, so that it can do its incremental compilation magic. But usually you don't need to touch those. The defaults are really good. If you want to pass additional parameters to the Scala compiler, there's this additional parameters collection. And if you want to use the old Ant backend, then you can again set Scala compile options.use Ant equals true. There are still some use cases for using Ant, and it's actually still the default for our Scala compile task to use the Ant backend, because sync is it's a very ambitious project. To incrementally compile Scala code is very, very difficult, and so for some people it still causes problem. Many people use it in production, but for some people the build fails when they use sync, and the Scala folks say themselves that there are still some things to sort out, simply because it's such a hard job to implement that thing. And in that case, you can always use Ant true. I probably will switch to use Ant false at some point. But here it's really good to have the fallback. Again, you get the same up-to-date check. That's not the same as incremental compilation. That's Gradle's business, the up-to-date check. How do you decide which Scala compiler you want to use? Same thing as for Groovy. You just declare a compile dependency, in this case on the Scala library, because that you need anyway on your compile class path. When you write Scala code, you need that Scala library on your compile class path. And from that, Gradle will figure out the corresponding compiler jar and use that to run the Scala compiler. So again, if, for example, if your production code is Java and only your test code is Scala, you would say just test compile Scala library, and then the Scala jar will never end up at on the compile class path of your Java code. And again, there used to be a Scala configuration, so you would say dependency Scala something, and you should simply replace the Scala with compile. And the Scala is now deprecated. You will get a deprecation warning if you use the Scala scope in here. Yeah, same story with the Scala-based plugin. You can now describe your Scala source code, exactly the same as Groovy base. Don't have to talk a lot about it. Also, Scala plugin, by default, very similar. You apply plugin Scala, at least the dependency on the Scala library jar, and we bring in the corresponding compiler jar with the same version and use that to run the compiler. So we have a little bit more to do here than for Groovy, because in Groovy, usually it's all the compiler and the library is one jar. I mean, there is also the separated one, and we can deal with that as well, but by default they're together, whereas in Scala, it's always separate. There's a Scala library and a Scala compiler jar. But we take care of bringing in the Scala compiler jar. If you do want to override it, you can always override these things on the task level, but usually the plugin does it just fine. So now joint compilation, exactly the same thing. You can have bidirectional dependencies. Java base class, Scala extends Java, Java extends Scala. And it's exactly the same story as on the Groovy front. How do you trigger that? Again, either you put all your Java and Scala code into source Scala, if you're happy with that, or if you want to keep the Java code under source Java, still have it joint compile, you again set the Java source directories to the empty set and add source Java to the set of Scala source directories. So then again, the compile Java task has nothing to do anymore, and the compile Scala task will joint compile your Java and Scala code. how does it work? Scala has a more sophisticated joint compilation, a better approach actually, a more stable approach. The Scala compiler includes a Java parser. So if your Scala code refers to some Java code and the Scala compiler needs the information, it gets it simply from the Java source code. It itself passes the Java source code and picks out all the information it needs to compile its own code. So first it passes the Java code, or actually it does that probably on demand. That allows it to compile its Scala code. And then once it has the class files for the Scala code, it simply invokes the Java compiler and passes the generated Scala classes on the compiled class path for Java C. And that's hopefully one day Groovy will always also do it this way, because this has shown to be the one right way. With the Groovy way of generating the stubs, you can sometimes get into catch-22 situations where the Groovy compiler after its passing doesn't have enough information to generate correct Java stubs, and then the Java compiler blows up. In practice, fortunately, it's very rare, but it can happen, and with this approach is 100% safe as long as the Scala compiler is implemented correctly. So that's the way to do it. Actually, Scala did it like Groovy until some time ago, and then they switched to this approach. Because this is theoretically sound, and that's why the Scala guys do it, because they always do what's theoretically sound. So one advanced use case you might have: how do you target multiple Scala versions? Maybe you happen to know that compiled Scala code is not binary backwards compatible. If you build an end-user application and you have the Scala runtime version under your control, you don't have to care. But as soon as you build a library for Scala, a jar or something that someone else reuses, you are in trouble. And why are you in trouble? Because if your user wants to use Scala 2.8, then you have to compile your library also against Scala 2.8. And if your user wants to use Scala 2.9, then you have to compile your library against 2.9. If you are a famous library, probably you will have users that use Scala 2.8, 2.9, and 2.10. And so you have to ship 3 versions of your library. Compile against the same Scala version. In all the Scala versions, even the minor had to match. Now they figured this part out, so for Scala 2.10, the minor doesn't have to match anymore, but it used to be really bad. Even for each release candidate of Scala 2.9, broke backwards compatibility. So they set up a system that whenever a new release candidate, like every 2 weeks, of Scala 2.9 came out, the most popular open source libraries, 30 libraries, were automatically built and published to their Scala repository, so that everyone could then test their apps, because it's a complete deal breaker for you. If you use a few libraries and you want to upgrade Scala, and one of those libraries hasn't yet upgraded and provided a jar compiled against the same version, you're completely host. You have to get rid of that library or not upgrade your Scala version. And imagine that with a minor version. You desperately need this bug fixed version of Scala, but there's one library which doesn't yet publish a jar for that bug fixed version. So that's really bad. Okay, they recognize that, so now it's a little bit better, but still 2.9 and 2.10 are not compatible. It's simply extremely hard to innovate a language and keep the runtime binary backwards compatible. Basically, no language on the JVM other than Java manages to do it, and Java doesn't evolve very much. I mean, so it's really hard. Groovy has the same thing. Between Groovy major versions, there are no guarantees between backwards compatibility. In Groovy, because they are quite pragmatic and don't touch code unless they have to, you might go lucky, but with Scala it won't work. Okay, so wouldn't it be nice if we could just say this? I have a Scala block here and say I want to target these Scala versions, and then Gradle should take care of the less and produce, let's say, if I'm a library, 3 jar files automatically for me. And then maybe I could set up some dependencies, like this is a Java library, so I want to use that as a compile dependency for all 3 of them. Then it's an interesting one. This is a Scala library, and as I said, there is a Scala C core for 2.8.1, 2.9.2, and 2.10.1. And so here I've invented the syntax _?. It means use the same version of Scala C as I'm just compiling against. That would be really nice to have, so that I don't have to list that all in the build script. If you compile the jar for 2.8.1, put Scala C core 2.8.1 on the compile class path and so on, it would be nice if Gradle could just figure that out. And then should you still want to put something on a compile class path just when compiling the 292 jar, then you could even say that, right? Bad news, it's not currently provided by our Scala plugin. Good news is Gradle is really extensible. So let's have a look at that. The most challenging thing for me is to find it. So here we go. So here we have our the same build script again, and now I've implemented that with today's Gradle as my own script plugin, right? So that I can use that syntax and Gradle will do the right thing. I want to have 3 libraries created and compiled against different versions of Scala, and it should even resolve it should use different versions of my dependencies depending on what I'm compiling against. So how hard would it be? And this is what I came up with. So it's a little bit of code, and maybe in some of the next Gradle versions we will ship that with Gradle, but it's perfectly, if you understand Gradle, it's perfectly possible to do that today. So what did I do? Okay, I'm relying on the Scala base plugin. Basically, I'm writing now my own Scala plugin, so I'm no longer relying on the Scala plugin, but I still want the capabilities of Scala base. So that's such a use case. Set up 2 class paths for the common dependencies. So if you want to put the same library on the class path of all 3 of them, you can just put it on the compiler runtime class path. Then I wrote a little extension, this here. This extends the Gradle build language. This allows my users of my plugin to say this thing here. This is in plain Gradle with the Scala plugin. You don't have this part of the language, but a plugin can extend the Gradle build language, and that's what I did here. That's the Potro basically, and then here I'm registering it under the name Scala, and this is why then you get this DSL for free. So here the Scala block is just configuring my Potro class, and then my plugin can make use of that information. Okay. So I have now this Scala extensions Potro which has a set containing the target versions. And then I iterate over all of them in a plugin. So for each Scala version specified in the build script, which in this case would be 3, I execute some logic. And let me quickly take you through that. Is that big enough in the background?